So we look at this sequence and we say to ourselves, all right, well, it's a sequence, that's great. And if all you need is the terms, no more work. You just do whatever you need to do with your sequence. But often we need to find a formula for the sequence. So when we want to find a formula for the sequence, we want to look for a pattern. Anybody spot a pattern of how you can describe this particular sequence? And right now, I'm only looking in terms of how would you get to the next term of the sequence from a previous term. Yeah. So a great thing with this particular guy is you totally get to the next term simply by multiplying that previous term by 2. I like to actually put in this same little notation that we did with our arithmetic sequences that says, hey, look, we are doing the exact same thing each time to go ahead and get the next term. Now, why would I actually do this more than once? There are some sequences where to get the next term in the sequence, maybe between these first two you'd multiply by 2, but in these next two you'd multiply by 3, and the next one you'd multiply by 4. And so it's not a constant number that you multiply by each term to get the next term. Those guys, there's not a problem with them, but they're not geometric. So the definition of a geometric sequence is you get the next term in the sequence by multiplying some stationary, some constant number by each of the previous terms. In this case, exactly what you guys said, where you have multiplied 2 by your previous term to get the next term in the sequence. Okay. Now, this particular relationship right here totally works for lots and lots of sequences. To make this relationship describe our particular sequence, or if you told somebody just this relationship and you wanted them to reproduce your specific sequence, you would have to tell them a starting point. So to go ahead and complete this description, I'll go ahead and put in that our starting point here was 3, and just like with the arithmetic sequences we did last time, I went ahead and started the index here at n equals 0. Could you start it at n equals 1? Yep, you totally could. Could you start it at n equals 400? I don't know why you would, but you could. Okay. Now, once you have this guy, which is a perfectly respectable way of defining sequences, maybe you realize to yourself, I actually wanted some sort of formula, some sort of function that's only in terms of n's for my sequence. Maybe that's because you actually need the 2,782nd term in the sequence, and you don't want to just multiply a bunch of 2's together for a long, long time. Okay? So just like with our example with arithmetic sequences earlier, I'm going to go through a strategy of how to build up to that general formula, that closed form or explicit formula where you have a function that's only in terms of n's. There is a shortcut formula for this, and I'll show that to you guys after we do the scratch work. I wanted to illustrate the scratch work here, or this procedure, this method, or the technical term is sort of like an algorithm, because it works on more than just geometric and arithmetic sequences. It works almost any time you have no clue what's going on with your sequence. So first thing that you do is you write out all your terms. I wrote out 5, but typically as long as you write out at least 3 to 4, you'll be able to see the pattern. Now, anybody remember what we did last time when we started doing this scratch work? The next step was to do something. Anybody remember what that something was? It's okay if the answer is no. So I would definitely always start from the top value and go down. The other thing that I'd recommend doing is actually describe how you got each of these next values. So this is where you're actually using what we've already discovered with this recursive formula. So if you started the secondary method, so this is really like a part 1 and a part 2. If you started down here below that second horizontal line, you wouldn't necessarily have this recursive formula up here at the top, but you would still be reproducing the recursive formula. So I'm not going to do anything with the starting value. So we're going to jump down and say, all right, well, how did we get 6 from 3? Well, that was exactly 2 times 3. How did we get 12? What was 2 times 6? How did we get 24? Well, it was 12 times 2, etc. In other words, we built a recursive formula, and now that I'm looking at this, I put the 2's here on a reason, but definitely feels backwards based off the recursive formula there. Okay. Now, once we're at this stage, we've exhausted everything that we can do with that recursive form. Okay? So the next stage is where you plug in. So you say, all right, well, 3, I can't do really anything with 3 yet. 6, well, 6 already looks like it's as good as it's going to get. But then you move down here to A2 or 12, and you notice we have both a 2 and a 6. Well, we already know 6 is 3 times 2, so I'm going to replace that 6 with a 3 times 2. Same deal with the 12. We know 12 is 6 times 2. Well, we just wrote it was 3 times 2 times 2. I'm going to replace the 12 with that expansion. Same deal with the 24. We just found 24 was 3 times 3 2s. I'm going to replace the 24 with 3 times 3 2s, and then the new 2 that came from that formula. Please note, when you're doing this on your own, except for like the first time, most people don't bother writing out this step right here. Okay? Why? Because as soon as you start seeing the plugin, you can start counting up how many 2s you actually have, and you can rewrite this guy in the much more efficient way with exponents. So 3 doesn't change. Wow, you can put in the exponent there. 6 doesn't really change. But here you can write 3 times 2 squared, then 3 times 2 cubed, then 3 times 2 to the 4th, etc. Okay? What often happens is most people will backfill those last 2. Well, they'll start off and just write the 3 and just write the 3 times 2, and then they say, oh, it looks like there's some pattern with the exponents. Let me backfill and put it in 2 to the 1st power and 2 to the 0th power. Because remember here, 2 to the 0th power, that's the same thing as 1. Or not really looking like it's there at all. Okay? Now, once you have something that looks relatively efficient, believable for all of your numbers, and that there's some sort of pattern, anybody have a guess on what the formula would actually be for AN? Don't overthink it. You can use any numbers you want. That's totally fine. You can use N, also totally fine. The only thing you're not allowed to use is you're not allowed to use these symbols, the symbols for the terms of the individual sequences. Yes, perfect. So for this one here, we notice there's a 3 in all of these formulas. There's a 2 raised to some power in all of these formulas. And this is where you look at these 2's, so all of these exponents, and you match them up to the n, the subscript you have over here. And notice they actually match exactly, which tells you this is 2 to the n, and then times the 3 out front. Now for completeness, you would tell your reader what n you actually start with. So this tells you, hey, start with n equals 0, and that'll guarantee you have the 3 here. If you'd start at n equals 1, you would actually not have this first term of the 3, and you'd start this sequence at 6 and go forward. Now, if you had actually at the very, very beginning decided that n equals 1 at the beginning here, that part would change, and the exponent wouldn't actually be n, it'd be n minus 1. So the formula will change depending on what index you start with or what value of n your first term is going to be associated to. Okay? Makes sense? Kind of feeling a little bit okay. Questions so far? All right. Notice this was the exact same procedure we did with arithmetic sequences. The only difference is here we had multiplications, and with arithmetic sequences we had additions. And let me go ahead and put it on this page. Unlike what we did last time with the arithmetic sequences, there is actually a shortcut formula for your geometric sequences. By definition, a geometric sequence, its recursive form is some constant, typically denoted with an R or a Q, times the previous, wow, and then I wrote a Q. Don't write a Q. Oh, no, I can't erase on this one. Or at least not easily. Just a second. That is one downside of dealing with PowerPoint. It does not let you use the back shortcut to actually get rid of something you wrote by accident. So geometric, by definition, some constant times previous term. So then if you want the closed formula, it turns out the closed formula is always, and let me go ahead and tell you that this thing starts at n equals 0. Closed formula would be your very first term times that R raised to the n. If you start at n equals 1, 2, something else, that formula changes, okay? So that is something that you have to watch out for, but in our course, we're going to be almost exclusively starting when n equals 0, okay? All right, so in terms of the next thing for us, the next thing on the agenda is to go and look at activity 2, okay? So if you didn't grab activity 2 from Canvas earlier, did not want to do that. We will go back to that slide when we finish activity 2. Okay? So let me pull up activity 2 for us and stop sharing that, because otherwise all you can see probably right now is a big yellow screen because I didn't push the button quick enough. All right, should hopefully see that now. So activity 2 is an activity on sequences. Just like when we have done a couple of previous activities in class, I'm going to throw you guys into breakout sessions. I went ahead and put together 4 of them, and you guys have already been randomly assigned into those breakout sessions already. So when I push the button that says start the breakout sessions, you guys should automatically jump in there. And as you guys probably noticed last time, there is a little bit of a delay in terms of transferring sound and yourself into the breakout sessions. So don't freak out about that if it doesn't happen immediately. But this here is the question. I'll go over this together with you guys before I hit the button to throw you into the breakout sessions. It's going to define a sequence based off of a description. So far we've only had sequences based off of where you're actually given the numbers, or that very, very first question that we had by way of a formula. Here it's another thing that you can see, a sequence defined by a description, so words. So AN, so let AN be a sequence, and it's going to be the sum of the first n positive odd integers. Positive, don't pick any odd numbers. Odd, technically odd numbers are integers, but this just made sure everything was very clear. So the first part just asks you to list out at least the first 4 terms. If you want to do more than the first 4 terms of the sequence, that's fine. I would recommend a chart, but that's up to you guys. And then it wants you to look at both the recursive formula and the closed formula for this particular sequence. And fun fact about this guy, the closed formula is actually easier for this particular sequence. It's easier to find the closed formula for this particular sequence than the recursive formula. One of the rare cases when that's actually true. Okay? Now, as a heads up, because I did this just this morning, so you may not have seen it because it's kind of behind the scenes. After you finish with this sometime today, do please upload your work from at least one of you from each of the groups that you go into. And what I've done in Canvas is for the activity 2 assignment, I went and set it up with groups, and I set it up so you guys could add yourself to whatever group you actually ended up, since WebEx was randomly generating groups and I didn't know who was going to be in what group before time, or ahead of time. Before time doesn't really work in that context. Okay? So any questions before we get started with this? Everybody got what they need? Seeing no frantic cries on your end, I am going to go ahead and throw you guys into the breakout sessions. All right, here it goes. Oh, one last thing. If you guys do have questions, run into problems, or get finished, do please send me a message. It's that button towards the top of the screen that you're about to see that says something along the lines of ask for help. It'll send me a message and I will come immediately and either answer your questions, or if you're done, actually if you're done, you either jabber or you can actually end the breakout sessions on your own. Okay? So here we go. 3, 2, 1, pushing the button. Deal with a set. Your set only keeps all of your distinct terms. So I think all of the sequences we've actually talked about so far had distinct terms. So for those guys, your set versus your sequence, it would only be curly braces that would change up. Okay? In terms of sequences that have repeated terms, the set would only be the distinct or the different terms. So for example, suppose you have the following infinite sequence, probably one of the more boring infinite sequences you could have. All of the terms are either positive or negative 1, and it alternates back and forth whether you have a positive 1 or a negative 1. So in this particular case, if you wanted to grab the set that corresponds to this sequence, any guesses what that set would be? Don't overthink it. What do you guys think? Oh, you're actually getting into the formula. Yeah, so the set is just the individual terms. So it would just be the 1 and the negative 1. And remember, order doesn't matter, so you could put the 1 first or the negative 1 first. But that would be it in terms of the actual set. That's it. There is no more. Okay? And that's all this set corresponding to the sequence is. Okay? So don't overthink it. It's literally just a list of all the different terms that you used in your sequence. And if you rearrange the order, no big deal. Now, the thing that we need to talk about is something called a characteristic function. Now, this part goes back to sets. Okay? You have to have a universal set in order to build this characteristic function. And what this characteristic function does is it takes some set in your world, in your universe, set A, I was super lazy, and then what you do is you look through all of the elements that are in your universe. And here's what you do. When you plug the element from the universe into your function, it checks, or that function checks, is this element inside of A, is X inside of A, or is X not inside of A? It's literally just a Boolean check. Yes, it's in A, no, it's not in A. Okay? And that's it for the characteristic function. Now, how do we use the characteristic function? We're actually going to write this characteristic function not in normal function notation. We're actually going to write it as a binary string. In other words, a finite sequence that only includes ones and zeros. Okay? So let us look at some examples. So suppose you have a very, very tiny universe. Suppose you only have the letters A through E in your universe. Suppose set A is A, C, and D, and set B is C, D, and E. Okay? Now, here's the thing that has to happen in order for you to use this characteristic function to encode your sets. Is unlike what we normally do with sets, where the order in which you write the elements in the set doesn't matter, the order is going to matter here. You fix the order of your universal set, so whatever order you start with, and I normally do it alphabetical if it's letters or if they're numbers, smallest to largest, and then however you've written them out, they stay in that position, okay? And that's going to make the rest of this stuff work. So here's what we're going to do. Oh, awesome, I put a fly in. So when we look at the first one, so if we want to look at the encoding of FA, so we want to encode set A using the characteristic function, what we'll do is we're going to have a grand total of 5 terms in our finite sequence, so only 5 of them. For element A, we're going to check to see if A is in the set A, capital A, or not. Then we'll check for B, then we'll check C, then D, then E. So instead of having these guys fly in, let's actually write them out. So what do you guys think? Is element A from the universal set inside of set A? Hopefully you're all thinking yes. And then you say, so we'll put a 1 for yes. Then we look at element B. B isn't there, so we put a 0. Then we look at element C. C is in A, so we put a 1. Element D is in A, and then 0 is not in A. That's it. Don't overthink this. Any guesses what the numbers should be, ones and zeros, for B? So this one here would do the same thing, but now instead of looking at the set A, we'd look at the set B. Yep, you got it exactly. So both elements little a and B are not in set B, and C, D, and E are in set B. That's literally it. Don't overthink this. Now, the nice thing about encoding your sets as these binary strings or these finite binary sequences is you can use them to find your intersections, unions, symmetric differences, etc. Okay? So remember here, if you're looking at the intersection of A and B, you are looking for elements that are in both the set A as well as the set B. Anybody have a guess how you could use these binary strings right here that we just created to get the answer that's also a binary string for the intersection of A and B? Yeah, you got it. So here, what do we need? If you have at least 1 0 in the position, you're going to put a 0 down in the intersection. And if you have 2 1s, you're going to keep the 1 because the 2 1s are when what? It's going to be dealing with when you actually have an element in both of the 2 positions. Okay. Now, anybody have a guess for unions? So union is you have to have elements that's in either B or A or both. Okay? So here, when you look at your binary string from A or B, you can say, all right, if I have at least 1 1, then I'm going to be in the union, and I totally messed up that last one. And I can't go backwards. Just a second. I need to erase. So here, the only time we had a 0 was when there were 2 zeros up there at the top. Now, anybody have a guess on symmetric difference? Symmetric difference was where you were in this, the element was in the symmetric difference if it was in exactly one of the 2 previous sets. Yes. So this one here, if we look at our 2 previous sets, in the first position, we have a 1 in exactly one of the 2 sets. 0, element B is in neither of the 2 sets. But for both the elements C and D, they're in both the 2 sets, so they are not going to be in the symmetric difference. And lastly, right here, we've got a 0 and a 1, that means it will be in the symmetric difference. If you're comfortable with binary addition, you can totally just add those guys together to get the symmetric difference where don't carry anything. So it's literally just a binary addition between the positions. So there the 1 plus 1 would equal 0, if that helps. If you guys are interested in normal addition, these are the actual properties. And these properties are based off of normal old integer addition. So here, if you're looking at the intersection, this is the same as multiplication. Why? Because if you have even 1 0, 0 times something, it's going to turn into 0. Okay? The only time you get the 1 for the intersection up here is if you had 2 1s. Now for union, this is where you add them together. But if you're doing it with normal integer addition, you'll get a 2 somewhere, and you really don't want the 2. So this is where you would subtract off that extra copy of 2, and anytime you got a 2, it pulled back to a 1. And then with symmetric difference, that A was terrible. This looks exactly the same as the formula for union, except here, if you actually had your guys in the intersection, you go ahead and subtract that off. Because you'd want to get anywhere there was a 2, you'd want to get rid of the 2 completely and turn it into a 0. Okay? But those properties are based off of normal integer addition. One of the nice things about being able to encode your sets as these binary strings is you can actually use binary addition. But I'm not going to go over that part today. If you already know it, you'll be able to recognize the relationships there. Okay? But that's it in terms of sequences. I don't have any more in terms of sequences. So any questions before we move on to our next topic? Notice the advantage of this, why we talked about it, was not because it was amazingly awesome in terms of the other stuff we've been talking about. The big reason of talking about this is it is 100% a way to encode your sets in a very manageable way. So for example, if you ever needed to encode your sets and put them coding somewhere, this is a way to do it. Not the only way, but it's a way to do it, especially if you have a bunch of sets in the same universe. All right, seeing no questions from you guys, I'm going to go ahead and get us to our next topic. All right, deal with that in just a little bit. That allows me to close it, so hopefully, okay. All right, I think that should be the only one displaying for you guys. All right, so the next section that we're going to get into, and actually let me go ahead and put the title in there, is dealing with various logic, what's also known as predicate calculus. So this is going to be the interplay between logical statements and sets often, and then we're going to culminate into what's known as proofwriting, and it'll be actually very formal proofwriting. And the thing behind, or the underlining concept behind all of this stuff, is trying to explain why something works, or if it doesn't work, why that something doesn't work. And these are the very formal ways of explaining why something works or doesn't work. So for today, we're probably going to get mostly terminology and some basic symbols and some basic truth tables is probably where we're going to get to today. All right, so a statement, also known as a proposition, is simply a sentence that's either true or false. So it's some sort of sentence that can be verified as being either true or false. So you'll notice in those parentheses it says not allowed to be a question. Why? Because a question, you can't verify if it's true or false. You could verify potentially that the answer to the question is true or false, though. Now, in terms of the truth values of the statements, we're going to care about statements that are either true or false, but it turns out there's actually more cases. You can have a statement where you have no idea if it's true or false. You can have a statement that you can actually verify that this guy is true. You can have a statement where you verify that it's false. And you can, well, I guess technically speaking, these are more sentences. You can also have a situation where the way that the thing is written, it has no meaning whatsoever. Just ridiculously crazy. Okay. So if you have a sentence that falls into one of these four categories, they will typically be tagged with these buzzwords in math. The first one is typically tagged as a conjecture. So this is like somebody's guess. They think this is true, but it hasn't been verified yet. And in actuality, this guy should be true or false. You just don't know yet. Okay? Now, if you have a statement that's been verified to be true, in math we call these guys theorems. They also have a bunch of other names too, but theorems is the big catch-all that says this is a mathematical fact, if you will. If your statement is false, these are typically the guys we don't want whatsoever. And if your statement doesn't make sense, that typically also means somebody screwed up somewhere along the way, and in actuality, we'd want to fix it. Okay. Now, something to watch out for, because this is something that is easy to miss, is in order for your statement to be tagged as a true statement, in all of the situations where that statement applies, you've got to be true. It has to work in all of those situations. This is the scenario where you have somebody telling you something, and there's exactly one time in the infinitely many possibilities where that statement fails. Well, that would mean that the statement is actually not a true statement because it doesn't work in that one situation. Now, if you needed the statement to still be true, what would you do? You'd say, this statement is true except for this one place where it doesn't work. There are ways to fix these things. So here are some really, really baby examples, and some ones that just got made up off the top of my head. Okay. So suppose you've got the following sentence. What do you guys think? Is this sentence true or false? And the sentence is, a right triangle has a 30-degree angle. What do you guys think? True or false? Or potentially one of the other guys where it's just worded badly. have to admit, I am now regretting not putting this into one of those little polls for you guys. That way you could make guesses and I could see if you were thinking. So there is one guess on the table. Oh, now there's more of them. Oh, I like it. There is no consensus whatsoever. So in order to be true, all right triangles must have a 30-degree angle. Is that something that is true? So, right. So do some right triangles have 30-degree angles? Yes, one of them. There is one right angle that has a one right triangle that has a 30-degree angle. That's the 30-60-90-degree triangle. Exactly. You're probably typing it before I started saying it. That one's one of your reference triangles. You probably saw it in like a high school trig class. That one is the one time where this statement works. But all other right triangles, they don't have to have 30-degree angles. They can have whatever angles they want as long as their other two angles sum up to 90 degrees. Okay? So this is a situation where you have one time when it's true and all of the other times when it's not true. So this guy will actually be false. And let me go ahead and put in my other sentences. Okay? Now, second sentence here that we want to check says the positive root of 9 equals 3 or is 3. What do you guys think about that second sentence? Does that seem true? Remember, to be true, it has to be true in all situations where it's applicable. Yeah, this one is actually true. Now, that second sentence is actually an example that I have done for several semesters with this particular class. And the original sentence I gave people didn't have the word positive. So positive root, make sure I don't have anything that's going to come in over here. Positive root means this. Why would you need that word positive in this sentence to make this guy true? Anybody have a guess? If we didn't have that word positive, what would change about this sentence? Right, so if you start off with 9 and you look at the roots of 9, that means you take the square root of 9 and you say, all right, well, what comes back? In other words, what number when squared gives you 9? Well, you totally have positive 3, that's true, but without this one here saying you're only looking at the positive root, you also have what's known as your negative root, and that's the negative 3. Have to admit, the first time I ever gave that one out, totally forgot about that word positive, and I was like, yep, it should be a true statement. It's my wonderful, beautiful example of that, and everybody was like, nope, it's totally false. Why? Because you forgot about this negative root. Okay? So watch out. They're really easy to miss if there's one exception to whatever it is you're saying. Now, the third statement. What do you think about that third sentence? That one says the sky has no clouds in it today. Now, I have to admit, if we stepped outside, we could probably figure it out. But yeah, that's one of those things. It depends on a lot of situations. It depends on what day it is. So if we took out the word today and actually put our date in there, that would make this a little bit better. But it also would depend where you're at. So like where I'm at, I see some clouds if I look out the window. But where you guys are at, maybe you're in a patch where you don't see any clouds out the window. So this would be something that, yeah, it's in your particular instance, you would be able to tell what's going on. But just as a blanket statement, you throw up your hands and you say, I don't know what's going on here. Now, any guesses about that last sentence? It says, the square root of a triangle is a circle. Yeah, don't overthink it. This guy here is just complete gibberish. First of all, what in the world is a square root of a triangle? A triangle is a geometric object. A square root is something you do with numbers. Exactly. So I tried to pick a sentence here that was Oh, I like your last comment. Yes, sometimes it might make sense. But something that looks very obvious that it has no meaning whatsoever. Typically, when you get sentences in the middle of your work or statements in the middle of your work that are complete gibberish, they're much closer to realness or actual facts than something like this fourth sentence right here. And it's just that you weren't thinking clearly, or maybe whoever sent you the supposed fact miscopied something. Okay? But yes, there are definitely times when you can create sentences that have no meaning whatsoever. Okay? All right. So let us jump now into looking at types of theorems. So these are where we're going to look at statements that would be shown to be true already. Okay. Now we already said that a theorem was some mathematical statement. Technically, other disciplines in math use it too. So some statement that can be shown or proven or verified to be true. Now, in order to verify that some statement is true or false, we're going to actually use logic in some very specific way, and we're going to go over the various methods to do that. And we're going to have a very set procedure of how do you explain mathematically why something is true or false. But before we get into that, different types of theorems. Do you need to remember these names? Nope, but you see them. If you look online, you'll see them. If you look in pretty much any sort of textbook or book, you'll see them. So this is what these different terms actually mean. If somebody just says, hey, I get a result, well, that one's more or less self-explanatory or a descriptor, and it's just a generic term here that says, hey, you did something, this is the consequence. Okay? Again, a fact, this is another generic term. Often, instead of using the word theorem, I'll use the word fact on lower level courses just because, not in our course, but in other courses, we just don't go over what some of these very formal words are at the very intro level classes, although I probably should. Now, here's where we actually start getting into the technical details. A proposition. A proposition is another name for a theorem. It means some statement that is shown to be true or some fact that somebody else has already proven to be true. Often, people will use the word proposition over the word theorem if it's a really important theorem. It's also, historically speaking, older than the word theorem. For example, in one of the courses I taught this spring, we looked at Euclid's Elements, which was written like over 2,000 years ago. Proposition was the word that they used way back then. Okay? So this is a older term. Not older that it's not used today, it's as in it's been around a while. Lemma, every so often you'll see the word lemma, and this is like a little small fact or a small theorem. It's typically a preliminary result. So it's something that you would have before the main thing you care about, and you typically use it to say why your main theorem actually works. So it's like a less important theorem. Now, a corollary is a direct result of some theorem or proposition. Actually, you could do it of a lemma, but normally it's just of a theorem or proposition. This guy here, when you were explaining why your theorem was true, maybe you found some secondary result. The corollary would be that secondary result. If you also found that you had, like, I don't know, some sort of formula, like, for example, think quadratic equation. If you actually plugged in one of the variables that you would normally pull from the quadratic equation and got some sort of simpler version, that would be your corollary. So it would be like a specific case of your theorem. And the last thing we have is something called a claim. This is essentially a conjecture. And this is about your statement before you verified if it's true or false. You'll typically use a claim either when you're verifying a theorem is true, or when you're dealing with verifying your lemma that you'll then use to verify your theorem is true. Now, at the end of the day, if you don't remember any of those terms, it's okay. But this will actually help you see the relationship between various facts, and your book uses all of these different terms. So these terms help give you insight in how the different properties and facts are related to each other. All right, questions so far, kind of making sense so far. I'm crossing my fingers, although none of you can see it right now. All right, seeing no questions come in, let us go on to the next thing. So the next thing that we're going to look at is specifically, we're going to look at our propositions and our logical operators. So here, we'll start off and we'll be dealing with our logical operators, and then after that, we're going to get into our quantifiers, and based on time, we are probably going to get somewhere in the middle of that. Okay? So when you're dealing with your statements, you can also combine your statements together. Okay? If you combine statements together in various ways, these are called compound statements. Some people don't bother with the word compound, they just say statement. It's a more complicated statement, but the buzzword compound statement just means that your statement could be broken down into smaller bits or smaller pieces. I shouldn't say the word bit with you guys. Okay? And then these smaller statements are combined together into that larger compound statement by some logical operators. Now there's a bunch of different logical operators. We're going to focus on some, but not all of them. Okay? So the first one is the negation operator, also known as a logical not. So if you start off with some statement, it's pretty standard to use the word P for statement, probably because proposition is another word for statement. It's also really common to either have that symbol P be either lowercase or uppercase. I have to admit, I think this is the only time when I have P as lowercase. Yeah, so that for me was just a typo because I normally make them capital letters. In words, the negation of statement P would be not P. And in terms of symbols, there's actually two common symbols that you'll see, either the little tilde symbol before a P or the logical not symbol that looks kind of like a hook right there. In terms of standards, often when people write them, they'll put the little tilde. You see this more in math. And often when people type it, you'll see this guy more. And honestly, if you're in any computer-related field, hint, hint, like 99% of you, this is more common in the computer world. Okay? Now, in terms of if we write out a truth table for one of these guys, and I could not get the two truth tables to fly in individually well at all, unless there was tons and tons of extra work. So a couple of them I've got flying in individually, but not all. So in this particular case, if you have your original statement P, if the original statement is true or if it's false, we'll look at all situations or all cases here. What happens if you negate it? Well, a negation does what? It just flips the truth value. That's literally it. Okay? Don't overthink it. Okay? Literally don't overthink it. The negation symbol acts like a negative symbol in integer mathematics or real number math. I really should have said algebra. Algebra would be the better way of saying that. Okay. The next logical operator is what's known as the conjunction, otherwise known as your logical and. So in this case, this guy, you actually legitimately are going to be dealing with a compound statement. So you have to have at least two statements. We'll let P and Q be our statements. So in terms of writing out the conjunction, this would be read as P and Q. Let's face it, most people don't bother with the word conjunction, they just say and. Okay? And in terms of symbols, it looks like an upside down capital V. Okay? One of the ways that I used to use to remember this one is the and symbol acts very, very similar to intersection. If you recall, your intersection symbol looks like an N, so it would look like this symbol right here for and, but rounded. If that helps, use it. If it doesn't, don't worry about it. So again, the entire truth table flew in at the same time. Oh well. So in this case, when you've got two operators, and let me put a line here. Typically when I write these out by hand, you'll actually put lines, and I'll actually put a double line normally there. Sorry about the wiggles. My hand definitely wiggled when I was drawing those lines. I typically put a double line here to indicate this is the stuff where we're checking all of the cases, and over here is all of the work. Personal preference, definitely. Okay. So when you have two original statements that you're dealing with, statement P could be either true or false, but notice if statement P is true, statement Q could be either true or false. which means we don't have just the 2 rows that we had from the previous situation with logical not. Here, we're going to have now 4 rows because each time P is true, we get true or false for Q, and then when P is false, we also still have those same 2 options of true or false. It does turn out that the number of simple statements, so builder statements that you have, so number of statements, I'm going to write it the wrong way. I need to erase that. That needs to be in the exponent. So 2 times the number of statements equals the number of rows in your truth table. Okay? And that way, that's a nice check to make sure you didn't accidentally miss a row. Now let's actually look to see what AND does. So in terms of logic of whether the truth value of P and Q is either true or false, here's what has to happen. Remember, in order to be true, you have to have all of your cases to be true. So this says we are looking at both P as well as Q. So if both P and Q are true, well, the whole thing is definitely true. But over here, if you have one of them true and one of them false, so you have true and false, well, that tells you that you have some situations that are false, and that will give you an entire truth value of false for the compound statement. And notice in the 3rd row, we also have 1 false and 1 true, so same result of a false statement for P and Q. And if both guys are false, false and false, still gives you false. Okay? Questions so far? Feeling okay so far? If you have a question when I'm saying something, just throw it out there, because I'm going to try to get through this last one and then one more example before we end for today. All right. So disjunction is also logical or. Again, lots of people just don't bother with the word disjunction unless they're logicians. My husband was trained as a logician in mathematics, and even he was saying, I don't remember which was conjunction or disjunction. I remembered I did them, but I don't remember which is which. So if you don't remember those 2 buzzwords, not a huge deal as long as you remember the and the or. So it's the same setup. You get 2 statements, P statement, Q statement. I was very carefully trying not to say the word and there. The disjunction would be P or Q, and in terms of symbols, the logical symbols here look almost identical to the one up here in and, except now that symbol, instead of being an upside down V, is a right side up V. The truth table will also look very similar. Notice here, in terms of all the possibilities of true and false for statements P and Q, I went ahead and put the same 4 rows. Why? Because we still have the same 2 simple statements. Okay? But now when we're trying to calculate the truth value of P or Q, we're going to do something a little bit different. We'll do the 2 easiest rows first. If your builder statements are true or true, well, everything was true. We're good. And if you have false or false, well, putting them together still gives you false. Okay? And that's actually the same in both the or as well as the and. But things change if you have exactly one of your statements P or Q here, true, and one of them false. Okay? So here, if P is true and Q is false, this is where the or comes into play. Or says, look at statement P. If you don't like statement P, that's fine. You can also look at statement Q. So or says, look either at statement P or at statement Q. So if statement P is true, awesome. We're not going to look at statement Q, and the whole thing is considered true. Now down here on this 3rd row, we look at statement P. It's false. We don't like it, so we say I'm going to disregard statement P, and we're going to then switch over to statement Q. In this case, we legitimately employed the P or Q, so we went over to Q. Q here is true, so we went ahead and said, hey, our truth value here is true. Okay? So those are the 2 differences between ands and or. Ands, you have to take into account both. Or is you're really just looking at one of them is sufficient. Okay? So both guys have to be true. Here, at least 1 true to give you a true value. All right. So let us look at an example. So suppose you were asked to create a truth table for the compound statement right here, we have not P and Q, and then that whole quantity or P. First thing is, well, how many rows should we have? And I would always recommend asking that of yourself first. In this particular case, we have exactly two simple statements. We've got the P and we've got the Q. So that means we'll have 2 raised to the power 2, or if you prefer, 2 times 2. So we'll have a grand total of 4 rows. The other thing I would definitely recommend doing is, after you know how many rows you're going to have, or maybe you do this before the number of rows, you want to figure out what your columns are. The first 2 columns, or the first however many columns, will represent your simple statements. So in our case, P and Q. If you flip the order, no worries. I went ahead and put the double bar here to indicate this is all of our work. The very, very last column is what you actually wanted to get to, and these guys are your helper columns. Just like with sets, order of operation still applies. So in terms of your order of operation, you have to do the stuff inside the parentheses first. And inside the parentheses, you've got to figure out what not P is before you can AND it with Q. Okay? So I went ahead and I just went inside of the operations. So the very first one we'd have to compute. So first we'd have to compute P, then we compute the stuff inside parentheses, and then we put it all together with P. Okay? So that's how I decided what the labels were on each of these columns. Once you got that together, I would recommend putting out all of your choices for your P and your Q, and these are actually going to be the exact same ones that we did before because we still only have 2 statements, P and Q. So P could be true or false, Q could also be true or false. Now, if we wanted to fill in the row of not P, any guesses what we would need to be doing here? Don't overthink it. What should we do? How would you decide what would go into that third column, in other words? Yep, you look at your column P, and you just say, all right, anytime I have a true, I'm going to flip it to a false. Anytime I have a false, I'm going to flip it to a true. So these guys, you're just going to reverse what you had in column P. And that's it. Now, when you get to this next column, where it says not P and Q, we're just going to be looking at these previous 2 columns. So if we look at these guys, this is an and remember with an and, the only time you're going to get a true value is if both the 2 pieces, both of you, the 2 statements you're building from, are both true. So if we look at this first row right here, what would be the truth value of the and statement? Would it be true or would it be false? Those are the only 2 options. Yeah, so this one would be false because we have a not P right here. And notice we have a not P on this second row too, so even without looking at Q whatsoever, we could go ahead and know that both of the first 2 rows have to be false just because not P was false for those first 2 rows. Now for the last 2 rows, not P is true, so there's a potential that we could get some true answers here. So what do you guys think? Row 3, should I put a true or a false? Yep, so this one should be a true because we have true and true. That'll give us a true. And last row is false and true. There was at least 1 false, so that one would give you back an answer of a false. Last thing, the last column here, we're going to look at the column we just built. So notice these guys build on each other. And then we're going to order that with the very, very first column. So I'm going to go ahead and put little arrows right there to indicate which ones we're looking at. So here with an OR, what happens? The OR says you're going to be true if at least one of the statements is true. Or the other way to think about it is the only time you're going to be false is if both your 2 statements are false. So in this first row right here, what do you guys think? Should I write down a true or a false? So this one should be true because it's true or false. Now, this second row has the same true or false, so whatever answer we had on the first row should definitely be on the second row. Third row is different. It's false or true. So what do you guys think? What should we put here for the truth value in the third row? Yeah, so this one's also true. It actually looks like we might actually get true in all the situations, and if we have true in all the situations, this would be a statement that could be called a theorem or a fact if we actually knew what the P's and the Q's were. So let's check that last row. Maybe we've got it. So then our last row says we have false or false. And what should we put for this very last guy? Our final truth value should be false, exactly. So unfortunately, this would be a case where the overarching truth value of this guy, it's true sometimes, it's false sometimes. Those guys are actually called conditional statements because sometimes they're true and sometimes they're false. Or if you had to just give a straight up truth value for it blanketed across all cases, you would have to say that, hey, sometimes it's false, so it cannot be always true. Okay. With truth tables or symbolic logic, also called your predicate calculus, with these guys, we actually break it up a little bit more. We say, hey, did we get true in all cases? Did we get false in all cases? Or is it conditional, where there's some truths and some false? The most desirable case is all truths. Okay? But we'll get into those terminologies as next time, as well as working more with this stuff next time as well. But that is everything for today. I will hang out for a few minutes if you guys got any questions, but I don't have any new material for you. Or I should say, I don't have any more material for us for today.